Wall, and this is my Lines of Charges lab for Physics 2212, which is an extension of the previous charge tapes experiment. The purpose of this lab is to estimate the charge found on a tape strip, this time improving our charge model. In the first lab, we modeled the tapes as a single point charge, getting an approximate charge of negative 1.27 times 10 to the negative 8th coulombs. In this lab, we will be more precisely approximating this charge as the distribution of charges along this line. The key ideas in this lab are Coulomb's law, electric field, line charges, which will be treated as a collection of point charges arranged in a line, and E-field superposition, which is the concept that electric fields can be added vectorially without affecting one another. Here's a diagram of the setup where we floated tape B by holding tape A below it. The separation distance between tape A and tape B, as well as the mass and length of tape B, are all shown to the right. To model a line of changes, I split the tape evenly into n individual charges, each with the charge of the tape's total charge over the number of sections. For each point charge on the top tape, I found the electric field due to each point charge on the bottom tape, and then added each of these fields together to find net electric field on each and every point charge in the top tape, which I solved for by making a double for loop. In my code, I set n equal to 100, where n is the number of point charges I split each tape into. The reason for choosing such a large number was to obtain as accurate a numerical value as I could. Larger n's means more accurate data, as we are effectively taking the integral of the given function more precisely. The green arrows shown in the diagram are the net electric fields for each point charge in the tape. The magnitude of the electric charge on the floating tape is 1.87 times 10 to the negative third newtons, and the magnitude of the gravitational force is 1.94 times 10 to the negative third newtons. Like Lab 1, the electric force in the top tape must fully balance out gravity for it to float, as seen in the white and yellow vectors. Our single point tape charge was negative 1.27 times 10 to the negative 8th coulombs. I adjusted the tape charge so that the electric force in the top charge balances out gravity, meaning I found the value of the tape charge which would make the forces equal to each other. We can find the proportion of the current electric force magnitude to gravity, which is 18% in this case. Since Coulomb's law has a positive linear relationship between charge and force, we can get the tape's charge by dividing by this proportion. This is how we get the approximated adjusted tape charge of negative 6.5 times 10 to the negative 8th coulombs. The magnitude is positive of that number. The first assumption does not apply, as tape B is static once it floats, so air resistance on a moving object is irrelevant to this lab. The second one doesn't apply either, as we treated each tape as a line charge rather than a point charge, and also didn't concentrate the charge at the center of the tape. Instead, we distributed the charge along the length of the tape. The third assumption does apply, as we did assume that the charges on the two tapes were the same. What if we had modeled each of our tapes as a single point charge like the first lab? Well, our single point charge model yielded a tape charge of negative 1.27 times 10 to the negative 8th coulombs compared to negative 6.5 times 10 to the negative 8th coulombs with our line charge model, which means there was an increase of over 4 times the estimated charge. These estimates differ because the line charge takes into account every infinitesimal charge, not just the two simplified point charges. This means greater charges needed to span all that distance with an equal electric force. The line charge model is closer to the real value because it is a more specific model, making less dramatic assumptions. Thank you.